All right. So again, thank you all for joining us today. I'm really happy to have Emily Witt as our speaker. And Emily, I guess, still very, you know, just uprising young scientist working at Johns Hopkins University. She received her PhD from Colorado University just last year. Immediately got recruited into the space lab at JSU. She's now currently an assistant research scientist working on a wide range of space experiments, I should say, starting from the sounding rockets that we're going to hear quite a bit about to CubeSats, to now she's also leading this new habitable worlds observatory spatially resolved UV spectroscopy science analysis group. So it's through that I've had the pleasure working under her leadership. So I'm very much looking forward to what she has to tell us today. So Emily,
Yeah.
take it away.
All right. Well, thank you, Shawen. As Shawen already mentioned, I am going to be talking to you today about one of the sounding rocket payloads that I have had the fortune of working on. As you can see from the slide, we've got a lovely rocket, very, very prominent. That will come up later in the presentation. But this talk is going to focus on observing shock dynamics in a supernova remnant with an integral field spectrograph. That integral field spectrograph was that sounding rocket payload that we launched into space. So this might be a little bit of a denser gas than most of you are used to working on, or than usually gets talked about, but it is relevant, I promise. Oh, come on, you were working so well earlier. There we go. All right. So we want to look at supernova remnants because supernovae are key to enriching the galaxy. On the left there, this is a picture of the small Magellanic Cloud. Most of those purple dots in there are supernovae or supernova remnants. And so you can see they are very prominent in the X-ray, and they are very much showing up and having a great impact on the environment around them. Many of you have probably seen this schematic or a schematic that is very, very similar. This is a periodic table of the elements where the origin of each element is shown. And you can see how many of these elements are formed in either dying high mass stars, which then could become supernovae, or in white dwarf supernovae themselves. So this is all part of the process of enriching the greater galaxy with metals, with metals. This is an all-sky X-ray image of the Milky Way. Again, the Milky Way is a very, very dynamic place, and some of the brightest spots and most prominent spots on this map are supernova remnants. I also flagged the Large Magellanic Cloud because there are a number of supernova remnants contained in that cloud. But all of these supernova remnants are spreading those metals out into the broader galaxy. And you can even see next to the Cygnus Loop supernova remnant, the Cygnus superbubble. This superbubble is thought to have formed from winds that are the result of supernovae and high mass stars. And you can sort of see that distribution of metals in that superbubble. I know all of you have seen this picture. This just shows how supernovae are part of the greater process of feedback in the cosmic ecosystem. As supernovae blow out their material and all of those metals, that material then gets blown by jets and winds, can get blown out of the galaxy into the circumgalactic medium, where it cools and recycles into the galaxy and gets recycled into new stars. And continues that process of feedback. So shock fronts in the supernova remnant are that point of transition between the ejecta and the ISM where that mixing first starts to happen. And when we're talking about mixing, I'm going to focus on two different types of shocks in supernovae. This is a very, very simple model Of course, the shock structure in a supernova remnant is far more complicated than this, and there are all sorts of different types of shocks. But for the purposes of this talk, we're just looking at two. The first type are non-radiative shocks. These are fast forward shocks associated with very hot gas, greater than 1,000 kilokelvin. These shocks are primarily observed in the X-ray, and these shocks come about as ejecta from the supernova propagates in diffuse interstellar medium gas. So on that picture on the right, we have that sort of surrounding circumstellar gas, which doesn't have a color. And then we have that forward shock wave in purple that is largely non-radiative shocks. And then we also have, as the gas cools, radiative shocks. These are much slower shocks. They become more prominent as the shock slows. They are associated with cooled gas, so less than 1,000 Kelvin. You see them primarily in the UV and the optical. The other thing about radiative shocks is that you see them as the ejecta propagates into denser ISM gas. So radiative shocks arise more quickly when ejecta is slowed down faster. And in that sort of schematic on the right, you're seeing radiative shocks in that sort of shocked ejecta going back into the cool ejecta. Now, as you might imagine, whenever you draw a binary, there is a point at which you have to transition from one to the other. And in this case, the transition between non-radiative and radiative shocks occurs at about 200 kilometers per second. Warm gas dominates this transition. We're talking 10 to 100 kilokelvin. And it's sort of that transition line between the purple and the orange in this schematic. Of course, no supernova is ever perfectly spherical like this one in the schematic, but we do the best we can. This warm gas is traced in particular by FUV metal emission lines. So I'm talking our good friend oxygen 6 at 1038 angstroms, carbon 4 at 1550 angstroms, and then a few others scattered in, but oxygen 6 and carbon 4 are the most prominent. So shock fronts evolve across the shock front, and one thing this evolution reveals is the morphology of the surrounding ISM. And this happens in shock fronts at scales that we could never observe just looking at the diffuse ISM alone. So in this particular picture, we have the XA region of the Cygnus loop. The background optical image traces the radiative shocks, and the overlaying magenta traces non-radiative shocks. So you can see in this particular picture, we have a forward X-ray ridge where the non-radiative shock has not slowed down fast enough to become a radiative shock. And then behind that, we have the main shock front where you're starting to see radiative shocks emerge. And there is a big gap between those two, it is thought, because there is a dense finger of ISM material that the shock has run into. So the material has slowed down quite quickly, and you get a big spatial disparity between the non-radiative and the radiative shocks. And then behind that main shock front, we have secondary shocks and cloud shocks going back into the supernova remnant. These shock fronts, these metal lines also reveal the energy structure of the shock front. So when you see different metal lines showing up, it's telling you that there are different conditions at that point in the shock front. So typically, if you're starting on the left out in front of the ejecta, this is oriented the same way as the last picture. And as you go right, you're going towards the center of the supernova. You have oxygen 6, which is very energetic. It operates at very high shock velocities and at high temperatures and energies is where it shows up. So you see oxygen 6. And then as the gas cools, you see nitrogen 5 and then carbon 4 starting to show up. But of course, again, these shock fronts tend to be quite complicated, and so it's not going to be pure oxygen 6 in one location or pure carbon 4 in the other. You have different elements showing up and blending together. The other thing we can probe with these shock fronts is dust destruction. This is particularly important because dust is processed over these shock fronts, and the mass distribution of the dust changes. I'm calling it dust destruction here, but what really happens is that you have these rather large grains of dust that are getting destroyed and reshaped into smaller grains of dust and then also into component parts. This happens in one of two ways. In non-radiative shocks, the mechanism that dominates is typically sputtering. This is when you have very high velocity particles that is chipping away parts of the bigger dust grain or potentially destroying it altogether. And then you have shattering, which is where you have dust grain collisions, and then that reshapes, and then those grains shatter into smaller parts. So this is particularly important because it changes the makeup of the dust that's available in the ISM that is then available for things like regulating star formation in the future down the line. So as a whole, we can see that shock fronts form a key environment in which material is processed in the galaxy and how energy is dumped into the ISM. So if we're going to pick just one supernova remnant to study, because for my project we had to, the Cygnus Loop supernova remnant is a pretty good supernova remnant to pick. It is a laboratory of many different types of shock fronts. The Cygnus Loop is 130 light years in diameter. It is about 2,400 light years away, and it's between 10,000 and 20,000 years old. That makes it a fairly old supernova remnant. However, because it is propagating into fairly diffuse ISM material, it has not lost all of its non-radiative shock fronts yet. So you still have non-radiative shocks showing up. And within the Cygnus Loop, we have the XA region. This is a region, as I mentioned before, where you have a dense finger of ISM material interacting with the ejecta, and that means you have a very spaced out difference between the non-radiative and the radiative shock front. It also makes the shocks very complicated, but that's what makes them interesting. The XA region, as you imagine, for a region that I would call interesting, is both well observed and well studied. I just called out two studies here, but Charles Danforth back in 2001 did a pretty in-depth study of the morphology and shock velocity, looking at lines in the metal lines in the far ultraviolet. And then Ravi Sankrit and his group did a study of dust destruction in 2014, primarily using infrared data. Now, the Danforth study in particular, and he raises it himself in the paper, struggled because they were stuck using data from the Far Ultraviolet Spectroscopic Explorer, or FUSE, and the International Ultraviolet Explorer, or IUE. Now, both of those payloads are amazing, great, did amazing science, but they weren't really designed for looking at extended sources. And that's because they're both point source spectrograph, which means you're looking at one location on the shock front and getting one spectra. And when you want to measure a full extended object over a large area, just doing one point and then doing another, and then doing another, and then doing another is going to take a long time and a lot of observing hours. FUSE alone observed the Cygnus Loop, the XA region, for 5 days to get 5 pointings. It was a lot of time, and it did not cover a whole lot of area. So if we want to observe shock fronts in the far ultraviolet, we're going to need something else. I already talked about point source spectrographs. Another solution is to use a long slit spectrograph, like with STIS. However, long slit spectrographs, even though they do give you some spatial information, wind up with the same problem. You might get information along the shock front itself, but you're only getting it in one particular direction. You're still going to need to take multiple observations with many steps of the long slit in order to build up a real map of the area. And of course, that's going to take a lot of observing time as well. What you would really like to do is integral field spectroscopy, which is where you are getting many pointings all at once, which give you many spectra that you can then reassemble into data cubes and effectively get an image of your shock front at many different wavelengths. So why hasn't there been a far ultraviolet integral field spectrograph before my project? Integral field spectroscopy is hard in the far ultraviolet. And this starts just at the base level with IFS technology. Traditionally, on the ground, you might use lenslets. Well, in the far ultraviolet, we can't use any transmissive optics. That light is just going to get absorbed and you are not going to see it. So lenslets are out. Another solution is lenslets and fibers, same problem, though I will mention that there has been some progress in the far ultraviolet with fibers, but it's not quite there yet for what we wanted to do. So we are left with image slicers. Image slicers are stacks of thin mirrors. They are all angled in a different direction, and that effectively carves up your focal plane into many long slit spectra that you can image all at once and reassemble into data cubes. This is also particularly pertinent because Habitable Worlds Observatory is considering using an integral field spectrograph either as a sub-instrument along with its multi-object spectrograph like JWST has with NIRSpec, or as its own standalone instrument. Now, traditional integral field spectrograph optical design does not work in space. This is a picture of the Muse spectrograph, which is an image slicer on the ground, one of the better ones, one of the best ones, I should say. And you can see that it's effectively swallowing the technician that is working on it. And so that sort of size is not going to be launchable into space. Now, then you might say, well, we have an image slicer in space. There is one on JWST with NIRSpec. However, that is an infrared image slicer, and infrared coating, optical coatings, are far more reflective than coatings in the far ultraviolet. Far ultraviolet coatings typically hover, I think the fuse was the gold standard, and that was around 60 to 70% reflectivity. And so you can imagine that reflectivity compounding on itself as you add corrective optics into the system. This means we need to get innovative if we want to see these shock fronts. So we need new optical design that does not include a lot of bounces. We need mirror coatings that are more reflective, which in our case are the mirror coatings that are out of Goddard with Manuel Quijada. And then we need large format FEV sensitive detectors that are capable of recording all of the many, many spectra that we expect to get. But if we're going to include all of this technological advancement, we're not going to be permitted to just launch an Explorer mission with all of this new stuff on. So that's when we turn to sounding rockets. Sounding rockets form a low-cost access to space. What they are is you build your payload, you bring it to NASA. NASA provides all of the guidance equipment and the motors, and you go down to your launch range, which in our case was White Sands. You launch the rocket. It takes data for about 5 minutes, and then it comes back down and lands in the desert. On the left here, we have a picture of a sounding rocket flight into an aurora. On the upper right there, we have a rough timeline of a sounding rocket launch. And then on the bottom, we have a picture of myself and my then junior graduate student, Alex Houghton. Alex is now the lead on this particular payload. With us as our telemetry engineer and our mechanical technician. They are both with NASA. And behind us is the Black Hawk helicopter. We got to ride out into the desert to get the rocket back. Because you get these payloads back, you can then take the technology out, iterate with the technology, try something better. If something didn't work as well as you wanted it to on its last flight, it can be replaced and launched again. The other advantage of these payloads is they are not trying to achieve orbit. They just go up, a parabolic trajectory, land in the desert. And that means that you are able to launch SMEX-size instruments at relatively low cost. And that lets you tolerate more risk and include new technologies onto your payload. Now, this is not that payload in the desert. This is a different payload. Some of you might be thinking, well, this is a shock front. You can use an integral field spectrograph, but could you tolerate a multi-object spectrograph? So there are other rockets that have developed other technologies, including OX Fortis. This is the payload that I am currently supporting at Johns Hopkins. The PI is Steve McCandless. The lead graduate student on this project is Mackenzie Carlson. And it is enabled with microshutters, which are lots of tiny doors. And in theory, you could use something like this to observe a shock front and use a slit stepping method like JWST does when it's using its MOS to do variation on integral field spectroscopy. However, again, it's going to take some time to do that slit stepping procedure. And in the case of a 5-minute sounding rocket flight, we're not going to have enough time to do that. So we decided to build the Infuse sounding rocket payload. And this was my payload that I built and worked on at the University of Colorado for my thesis. Infuse was the first traditional far ultraviolet integral field spectrograph. It's composed of a Cassegrain telescope. That telescope focuses light onto an image slicer. You can see that off to the left with all of those tiny mirrors angled in a different direction. Each of those mirrors goes to one grating in the far ultraviolet grating array. This is particularly important because we are cutting out a lot of the reconfiguring and refocusing objects by powering those gratings and giving each slice one grating. They're all replica gratings. They are all identical, and that meant we were able to keep the cost within a sounding rocket budget. That light, those spectrograms, is then registered on the MCP detector. This, in particular, for those of you who may want to know, was a cross-strip detector, which basically means we were able to a far faster readout than traditional MCP delay line detectors. This payload also included new mirror coatings out of Goddard that are being baselined for Habitable Worlds Observatory, and the detector is also of the type that is being baselined for the MOS on Habitable Worlds Observatory. So, like I said, one grating goes to one spectrogram. Each of those spectrograms on the bottom left there is effectively a long slit spectra that can be chopped up into spatial resolution elements. We have 26 of those. And then those long slit spectra can be reassembled into images at different wavelengths. So on the right, the background there is just an optical image of the X-ray region from DSS-2. Overlaid in cyan, we have the theoretical Infuse pointings. This is what we expected to see for Infuse if it were to get the best performance that it had. In yellow there, we have the fuse pointing, so you can just see how many infuse spectra we are able to get compared to one fuse spectra for each of those yellow squares. And then we have some predicted infuse data down at the bottom. Now, nothing is perfect, of course, when you bring your ideas from theory to reality, and we had to build this payload. So on the left, there's a fancy zoom in of our grading array, and there's a few people who worked on the project. One of the nice things about sounding rockets is that students are able to work, and indeed, I was a graduate student. I was running all of the day-to-day operations of this project, and you actually get to handle equipment that you would never get to touch on a bigger mission. So that was all nice. On the bottom left, we have one of our undergraduates who is now continuing to work at the lab as an engineer. We have our electrical engineer in the background on that picture of me installing the detector. And then we have our lab tech, Alex, and another one of the undergraduates either celebrating or waiting for the detector install. I can't quite remember when that picture was taken. So once it was all assembled and we got light down the payload, we were able to do things like image an extended object in the lab. So this is an intentionally out of focus spot in Lyman alpha that we put down the payload, and you can see how each of those slices from that image were reassembled to make that picture of the spot. So ideally, that is what we were going to do for the X-ray region of the Cygnus loop. And then we launched it. Launch was a blast. You can see our team in the upper left there, some pictures from launch night. Myself and my advisor, Brian Fleming, who was the PI of this instrument. Someone decided to be very funny and to put me on top of my name above Brian's on the launch list for the night. I have no idea who that was. And then in the middle, we have a picture of the sounding rocket itself launching and going up. Now, launch night was not without its problems. One of the things they have to do on launch night is they have to clear out this highway that runs next to the White Sands base and make sure there's no one there, just in case a rocket were to fall on them. And the way they do that is they send one car one direction and one car the other direction. And one car went one direction and saw an RV on the side of the road and saw the lights were off, thought it was abandoned. The other car came in the other direction, saw the lights were on, and knew we needed to get them out of that zone. So between that evacuation and then a subsequent weather balloon issue, our payload wound up sitting on the rail for over 2 hours longer than expected. And while it was sitting on the rail, it was off of its vacuum pump. This vacuum pump keeps the payload from accumulating gas inside of it. Unfortunately, 2 hours was just too long. We had gas accumulate and get trapped in the detector. So when we launched and the detector turned on, we saw nothing. Fortunately, or this talk would end right there, the gas did slowly work its way out over the course of the flight, and we were able to get some data. However, instead of the 300 seconds of data we were expecting, we got 19.4 seconds of data. And this is what 19.4 seconds of data looks like. It's not a whole lot. The most prominent feature on this image is some geocoronal Lyman alpha that's not scientifically interesting for this flight. But I was still able to extract some data from this and make it work. So this is the infuse pointing with all of the long slits oriented along the shock fronts. And we were able to see 3 or 4 spectral lines. It kind of depends on how you count. We were able to see carbon-4 and oxygen-6, which are both quite bright and are resonant lines. And we were also able to see a third line. This line was a blended line. It was a combination of oxygen-4 and silicon-4, which meant, if you made some assumptions about what those two are supposed to be in relation to each other, you could pull those out. So it was 3 or 4 spectral lines. And you can see, looking at the image, we have carbon-4 on the right. Its most prominent emission is coming from back, fairly far back within the cloud. We also have oxygen-6, which is set a little bit farther forward, and then the oxygen-4, which is close to the oxygen-6. So remember, we want to learn about the morphology, the energy structure, and the dust destruction that is occurring across this shock front. So let's start with the energy structure. And for that, we are really looking at the shock velocities in the supernova remnant. Now, when Danforth was doing his observations, he found shock velocities in line with about 130 to 140 kilometers per second. And that is much lower than expected, simply because oxygen-6 is hanging around. Now, when we did the measurement, we found shock velocities in the range averaging out to about 100 to 120 kilometers per second if you measured using a ratio of carbon-4 to carbon-3, and shock velocities in the range of 90 to 100 kilometers averaging out if you're looking at the oxygen-4 to oxygen-3 ratio. Now, you might have noticed I mentioned oxygen-3 and carbon-3. We did not see those lines with the infused payload, though we did expect to see oxygen-3 and would have if we'd had a longer flight. Instead, I pulled those lines from the old IUE data, which is why those pointings which is why it's not continuous along the shock front, and you're just seeing shock velocities where those IUE pointings are. Now, there are points in the shock front where you see higher velocities that are more in line with what you would expect from oxygen-6. But in general, the shock velocities were a little low. we would expect much higher shock velocities, higher than 170 kilometers per second. And that is likely due to the fact that because there was so little infused data, I had to quite aggressively bin it up. And that meant that gas at a much slower shock velocity was likely in the same resolution element as gas with a much higher velocity. And when those blended out, the lower velocity gas dominated. So we're not seeing quite what we expected to see, but this is likely an instrumental issue and could be fixed had INFUSE had its full observing time. So moving on, the INFUSE was also able to tell us a little bit about the morphology of the shock front. In order to understand the morphology, first I needed to locate the main shock front. Again, INFUSE was binned quite aggressively, so it was difficult to do with the INFUSE data alone. Instead, I turned to Hubble data. This is from Wide Field Camera 1, all the way back to Wide Field Camera 1. This particular image on the left is H-alpha data, and I traced out that, and using the H-alpha data, I was able to trace out that main shock front. The little boxes in there are IUE pointings that also help me find the shock front, and then come up with a solution for how far away from the shock front you were at any given point in the INFUSE map. And what that enabled me to do is to take slices perpendicular to the shock front and see how the metals that we observed were changing relative to each other. Oxygen 6 and the silicon 4, oxygen 4 line were well co-located, while carbon 4 was set quite a bit back from the other two. This was a little bit this was initially a little bit odd, but when you compare it to the oxygen 3 map, which you expect to align with carbon 4 because oxygen 3 has the oxygen 3 optical line has a similar ionization energy, you find that they match each other. So we can at least say that the carbon 4 is likely located well. With the oxygen 6 and the silicon 4, there's a few things that are possible. Oxygen 6 is, you see it showing up at far higher energies. It needs higher energies to be excited. And carbon 4 is highly processed in dust grains, and you get a not insignificant contribution to that carbon emission from dust grains. So it's possible that that is also having an effect on where these metal lines are showing up. So then we move on to the dust destruction itself. But carbon is not only found in dust grains in the shock front. You have contributions both from carbon that was previously in the gas phase and carbon that was trapped in the dust, and that carbon is now being liberated off of dust grains as it's processed through the shock front. So due to line of sight effects, you need to cap the carbon 4 emission at the shock front, effectively at the shock front. You can more easily measure how much carbon is in the gas phase at the shock using the ratio of carbon 4 to helium 2. At the best aligned pointing of IUE, again, this is using old IUE data, 77% of carbon enters the shock in the gas phase. However, if you go back to the original IUE spectrogram, so not the processed data, and look at only carbon 4 that is co-located with helium 2, you reduce that value to about 50%. So you would expect 50% of your emission to be coming from carbon in the gas phase and the remaining emission to come from carbon that has been liberated from dust grains. So we want to understand a little bit about how this dust is being processed, and that involves modeling from the H-alpha data. H-alpha data is directly related to the flux of particles passing through the shock, and what that means is making some assumptions about abundances, you can then measure how much carbon has been liberated from dust grains. So again, that's our old H-alpha WIFC. I was going to say WIFC3. It is not WIFC3. Wide field camera data, and then we have our INFUSE carbon 4 data on the right. So using the H-alpha data to predict what we would expect to see with the INFUSE carbon 4 data, we get something like these two images here. The curved images, very pixelated images, are predictions of carbon-4 emission from the H alpha data, while the contour lines are the infused carbon-4 data. And the modeling revealed that we had two good fits for this model. In one fit, we had a high neutral fraction of hydrogen at the beginning of the shock, and that correlated to the upper bound of uncertainties that we saw in the infused carbon-4 emission. It will probably not surprise you that infuse had very large error bars as a result of the 19.4 seconds. The other model that fit well was a low neutral fraction of hydrogen and matched with the lower bound of the infused carbon-4 emission. And that lower neutral fraction is more in line with what we would expect given other studies of other shock fronts elsewhere. So I would say that one is more likely to be the case, but it's difficult to say with the state of the data as it is. But all that means is that we have more work to do. So INFUSE is going to absorb more shock fronts. It's going to observe the Vela supernova remnant. This assumes a southern launch opportunity in the next few years. INFUSE initially proposed and was granted this opportunity, but with things the way they are, it's difficult to say when that will happen, hopefully within the next few years. The Sprite CubeSat, which is a CubeSat out of Colorado, will also launch in 2026. It will observe the Cygnus loop, and because it is a orbital platform, it will have a lot more observing time, and so will not be hampered by 19.4 seconds of data. I also intend to conduct observations with COS and STIS to help better constrain the dust destruction data, and particularly the resonance effects. The reason there was such a large, one of the reasons, other than the limited data for carbon-4 having such a large error bar, was because it is a resonance line, and you do have to account for that. And that's going to just add uncertainty onto your data. So we also have future far ultraviolet missions which will expand our capabilities. Now, not all or even most of these instruments are intending to study shock fronts in supernova remnants, but they are expanding what is capable and what can be studied in the far ultraviolet. These include Habitable Worlds Observatory, ASPRA, which is a pioneer, which is going to be launching next year. They're looking at FUV emission in the circumgalactic medium of nearby galaxies. DISCO, which is a SMEX mission concept that will be proposed to whenever the SMEX AO comes out, hopefully in the spring. And then IMPI of the Juniper CubeSat, which is selectable currently. No APRAs were selected. We're currently waiting on that one. But it is also going to be studying FUV emission in the CGM, slightly differently than ASPRA, though. So I will also take this opportunity, Shawen mentioned it at the beginning, but to plug the fact that we have a spatially resolved UV spectroscopy science analysis group. This is in support of HWO. We're not just looking at integral field spectroscopy, we're looking at multi-object spectroscopy as well. The goal of this SAG is to bridge the gap between science and technology. So we are considering science cases with thought to their technical requirements, and how they fit together, how those requirements overlap, and how they function within HWO. We meet every other week. I will be presenting at the Winter AAS 2026 during the COPEG Splinter session. We are hoping to have a workshop, and we will be presenting a white paper at the closing of the SAG. So if you are interested, please feel free to contact me and get in touch. We would love to have you. And with that, I will say thank you and take questions.
Thank you. That's really fascinating. I guess I will just give people a couple seconds to. Great, we have one hand. Drew, why don't you unmute yourself?
Yeah, hi Emily. First, nice talk. really cool to see what you're able to do with very limited observation time on Infuse. I've been there, so I know how that
Oh
goes.
yeah, oh yeah.
Uh, I was wondering, could you talk a little bit about, I know Infuse was an image slicer. You also kind of showed, long slit spectroscopy. What sort of challenges or potential limitations did you experience with the image slicer approach that might make, or, alternatively, in what cases do you still think going with slit spectroscopy is still a useful way to go?
Yeah, yeah. I mean, one of the challenges with integral field spectroscopy in general is detector real estate, right? You only have so much, even with these large format detectors, you only have so much detector that you can take up. And you have to balance your spatial resolution with your spectral resolution. So if you want, say, really high spectral resolution, you can do that much more easily with a long slit spectrograph. And then you could potentially step that across whatever your extended object is. In our case, we were looking at metal emission lines. We didn't need particularly high spectral resolution, but I can absolutely see science cases where you would want to do that slit stepping so you can preserve that resolution.
Great, thanks.
So to follow up on that, I actually didn't get what was the special resolution for Infuse?
Oh yes, I didn't share numbers in this particular presentation. We were fairly low. We were around 200 result was our resolving power. This is partially because every again, I was very aggressive with the bidding. But it was also because we had a bit of an issue with our telescope mirror mounting, and we were not able to correct that in time for our sounding rock for our launch. I think what was but our design spectral resolution was not that much bigger. I think it was less than 500 or so. So this is a very moderate, low to moderate resolution spectrograph.
Mm-hmm. Mm-hmm. Uh, so another follow up, because in your slide you actually mentioned nitrogen 5. I was
Yes.
wondering, did you detect, or is it covered or is it blended with lemma alpha?
So nitrogen 5, the particular nitrogen 5 line we were looking at, well, no, it's nitrogen 5. No, it was not blended with Lyman alpha. We were not able to see it. We expected to, and I think I have, let me see if I can find that predicted image. Yeah, come on. So you can see our nitrogen 5 is just off from Lyman alpha here. But again, that's one that we would have hoped to see, but we're not able to.
Uh-huh. But with longer integration, in principle, you will be.
Yeah, in principle, with longer integration, this was the prediction for a 300-second sounding rocket flight, so we would have expected to see it.
Great. I don't know if anybody else, because I can ask you more questions, but I don't think we want to take up everybody else's time. Maybe one last question from me. So from my as a user, from the user's perspective, I don't quite get the actual physical limit on the blue end of the spectrograph or detector. So if we want to push below, say, 900 angstrom, even just from the point of view of bridging the gap to X-ray, so we can get a little bit of extreme far UV to get into a little bit of soft X-ray range. Is that a possibility?
Right. So that would be difficult. Infuse itself only went down to 1,000 angstroms. Now, if you wanted to push farther than that, one of the problems is that the mirror coatings that they're working on at Goddard, so the enhanced lithium fluoride and the xenon enhanced lithium fluoride, those have a significant drop off in reflectivity around 100 angstroms. So we're talking going from nearly 90% or 90% reflectivity down to a couple of percent. And that's just a limitation of the materials themselves. If you did want to push down, There are other mirror coatings that don't experience that drop off. So Fuse got around that problem by having two of their 4 channels be coated with silicon carbide, which has a much lower reflectivity overall. It's, I think, in the neighborhood of 30%. But you don't have that drop off, and you can push down to that 900 angstrom range. Now, whether you sacrifice other science elsewhere, so there are obviously trade-offs there.
Sure, understand. All right. If no more questions, well, thank you again, Emily, for a very enlightening talk. We don't have enough talks like this. But anyway, for the rest of the group, thank you again for joining us. We will see you back next year in 2026, January 2026. Thank you.
Thank you, everyone.